Hello to this explanation video on modeling in 3D using Monte-Car's EmbeddedMontiArc math. The Monte-Car language family is powerful and extensive. In this video we will discuss 4 of its components, which are marked red here. We will start with EmbeddedMontiArc and show how MontiMath is used to extend EmbeddedMontiArc to EmbeddedMontiArc math. Finally, we will discuss the stream language, which is used for testing. EMA is a component and connector-based modeling language. This view shows a component with 2 input and 2 output ports. And here we have the corresponding code in EMA, but with a missing implementation. To enable a powerful implementation, we present MontiMath, which can be used as a standalone language. The box shows 3 examples of its capability. You can define and access matrices and also declare units. Units are a very helpful feature in order to prevent mistakes. The third line also shows how to define ranges. Extending the previous example leads to the following code. Since this component is for illustration purposes only, the implementation is kept very simple. In order to test EMA models, we define input values and also determine the expected output values. The sequences are separated by the word tick. This example shows a simple adder and shows also how to define tolerance ranges in line 4. Now we take a closer look on the architecture and implementation of our Autopilot model. This auto-generated visualization shows its 2 main components. While behavior generation determines the what, motion planning computes the how. The simulator provides various input values and expect values for engine, brakes and steering. In the editor, you can see the corresponding code with ranges and units. The 3 subcomponents are accessed by using instances. The first component is a simple compass to compute the car's orientation. The implementation of the other 2 main components I'll explain in the following. Depending on the car's current position, which are given by the input values of behavior generation, the path on the given trajectory can be trimmed. To trim the path, we check how many points are left. If there is only 1 point, then there is no trimming needed. If there are more, we iterate through them and take the closest point. All trajectory points before this one can then be trimmed. Once the path is trimmed, we want to calculate the motion commands for our way to the point. First, we have to determine the signed distance to trajectory, which is done by the shown formula. Now that we know on which side of the route we are, we use Bezier interpolation to calculate our way there. Here we distinguish between 2 options. Either there is 1 point left or there are more points. If there are more points, the algorithm will shorten the route. Now that we have determined the desired direction and velocity, we have to calculate the engine, brakes and steering. If the direction has not changed, we can keep the last steering value. Otherwise, we compute the new value by adding the signed angle and the trajectory error. Engine or brakes are remaining and calculated using a classic PID controller. Subcomponents calculate the PID parameters, error and so on. Finally, we make sure that the computed values are within the bounds or the capability of the car. This was a short overview of the project. Please visit the IDE and take a look at the implementation of the other components. You will notice that component and connector languages are pretty understandable once you understood the whole concept.